Let's now switch gears and let's talk about reduction oxidation reactions. Let's first talk a little bit about oxidation state, and then we'll talk about 4 different reagents used to oxidize alcohols. Reduction oxidation reactions are fairly easy to see in inorganic chemistry, and you had lots of examples of this in Gen Chem. For example, if I reduce chromium 6 to chromium 3, I actually gained 3 electrons, so I went from +6 to +3. Oxidation of copper, so copper 0 is metallic copper. If I oxidize that, I actually lose 2 electrons, and I go to copper +2. For organic compounds, we can still do this same methodology, but we can look at an organic compound and tell very readily if it's been oxidized or reduced. If I oxidize an organic compound, I either gain an oxygen or O2, or I gain a halogen, or I lose hydrogen. It sounds like a lot, but in general, most oxidation reactions in organic chemicals, I just increase the number of carbon-oxygen bonds. And reduction is just the opposite. I decrease the number of carbon-oxygen bonds, or I gain hydrogen, I lose oxygen, O2, or a halogen. Let's look at the schematic here. So here I have an alkane. If I add one more carbon-oxygen bond, I've oxidized that carbon to make the alcohol. I can oxidize that again by creating 2 carbon-oxygen bonds. This is going to be an aldehyde. If I oxidize that again, I have 3 carbon-oxygen bonds, or carboxylic acid. And finally, if I oxidize that, I get 4 carbon-oxygen bonds, or CO2, which is burning. So combustion is actually an oxidation reaction, and that's why I need O2 to actually burn wood. I need to create from my alkane all the way up to my CO2 molecule, the most oxidized. Let's look at the oxidative states of carbon, and let's start with primary alkanes, secondary alkanes, and tertiary alkanes. If I oxidize a carbon on a primary alkane, I'm going to add one more carbon-oxygen bond, and that's going to be an alcohol is the next oxidative state. Oxidize it further, and I get 2 carbon-oxygen bonds, or the aldehyde. Oxidize it again, and I get 3 carbon-oxygen bonds, or the carboxylic acid. If I oxidize that, I'd actually get CO2, and that would be a combustion reaction. If I take a secondary alkane, so one of the carbons here, and I oxidize that internal carbon there, I get a secondary alcohol. I oxidize that again, and I get the ketone. And I can't oxidize that any further unless I burn it and get CO2. If I look at a tertiary carbon and I oxidize that, I go from the tertiary alkane to the tertiary alcohol. I can't create any more carbon-oxygen bonds unless I break some of these bonds here, and the way to do that is to burn it or to get CO2. I can look at the opposite way too. If I reduce a molecule, I can reduce the number of carbon-oxygen bonds, so I can reduce a carboxylic acid to an alkane, or a ketone to an alkane, or a tertiary alcohol to an alkane. That's a reduction reaction. Let's actually count electrons and see if that is actually the same as inorganic compounds. Okay, so typically when we think of reduction reactions, we think of the acronym oil rig. Oxidation is loss of electrons. Reduction is gain, oil rig. And so let's see if that holds true just by our new definition in organic chemistry is creating more carbon-oxygen bonds or losing hydrogen. So let's go up here to the alkane and let's assign oxidative states to the carbon. So I know hydrogen is always +1. If hydrogen is +1 and R is just another carbon. That means that this carbon had to have an oxidative state of -3. If I oxidize it, we can do the same thing. We're going to assign +1 to all my hydrogens and -2 to every oxygen. That means that my carbon had to have been a -1 there to make this all neutral. If I oxidize that again, my hydrogen is going to be +1, my oxygen is -2. Therefore, this carbon had to have been a +1. And finally, if I come out here to my carboxylic acid, assign +1 to my hydrogens, -2 to my oxygens, that means my carbon now had to have been -3. Because +3 -2 -2 +1, that equals 0. And so in other words, I've gone from a -3, I've lost electrons around my carbon here, and I've gone to +3. Oxidation is loss. So in fact, that does hold true. I've actually oxidized that carbon. I've oxidized the whole molecule here. One thing that we don't include in oxidation reductions is a loss of an H+, a loss of water, or a loss of HX. So this is neither an oxidation or reduction reaction. So going from carbon -3 to carbon +2, that's an oxidation reaction. So here are some ways we can do some oxidation reactions. One of them is a dehydrogenation. Hydrogen, if I lose hydrogen from an alcohol, I'm going to form a carbonyl carbon. So I've gone from one carbon-oxygen bond to two carbon-oxygen bonds and lost hydrogen at the same time. One way to do that is take a copper oxide catalyst and some heat. In fact, over 300 degrees Celsius, I can do that oxidation reaction. Another way to do that is to use a copper zinc catalyst at 400 degrees. Unfortunately, what we see is that most organic chemicals either melt or decompose at such high temperatures. So this type of dehydrogenation reactions have limited capabilities in most laboratory settings because the molecules just don't survive at those temperatures. One of the most common methods of oxidizing organic molecules are using molecules like chromates. So chromates actually are oxidizing agents. So they get reduced and the organic compound gets oxidized. Notice there's a bunch of oxygens on here. So secondary alcohols are oxidized to ketones by sodium dichromate in sulfuric acid. The active reagent is probably H2CrO4. That's a little bit of a hypothesis by scientists. One of the interesting things, though, is that when I do this chemical reaction, because whenever I oxidize something, I need to reduce something. So the chromate is my oxidizing agent. It gets reduced to chromium-6, and when it gets reduced to chromium-6, it looks sort of like a dark green. So I know the reaction has occurred. So if I take a secondary alcohol, I expose it to sodium dichromate and sulfuric acid, I form the ketone. If I take cyclohexanol, another secondary alcohol, in this case, I'm just going to list this as sodium dichromate and sulfuric acid, I get 90% yield of the cyclohexanone, a ketone. So here's what scientists speculate is the actual active ingredient when I use sodium dichromate as an oxidizing agent. I take sodium dichromate, I put it in a solution of water and sulfuric acid. I actually form this chromic acid molecule that actually does the oxidizing, creating more carbon-oxygen bonds to an alcohol. I can also generate this chromic acid by taking chromium trioxide and sulfuric acid and sort of generate it in situ. This is actually what is known as Jones reagent. I get the same product whether I use Jones reagent or sodium dichromate. I get that same active species here, which is the chromic acid, which is the oxidizing agent. Let's look at the reaction mechanism for using chromic acid as an oxidizing agent. Here I have a secondary alcohol. Here I have chromic acid, whether that chromic acid came from Jones reagent or whether it came from sodium dichromate, I get that same product. I form the chromate ester because my chromium is an electrophilic molecule, so I form the ester with my carbon here and oxygen. Then my water acts as a base to deprotonate my carbon because that makes my chromate ester is a good leaving group. And when I do that, I add one more carbon-oxygen bond, in this case forming the ketone and my chromium 4, which can then go on to react again. How about primary alcohols? If I take cyclohexylmethanol, which is a primary alcohol, I react it with sodium dichromate and sulfuric acid. I actually oxidize it all the way up to the carboxylic acid. So this is the most oxidative state without going to a combustion reaction. This is considered a very strong oxidizing agent. This reagent does not stop at the aldehyde because it keeps on oxidizing it up to its carboxylic acid. If I want the reaction to stop at the aldehyde, going from a primary alcohol to a aldehyde and not going on to the carboxylic acid, I have to use different reagents. One that has been found to be very useful is this pyridinium chlorochromate complex, where I actually react the chromate with pyridinium, which forms this sort of poisoned chlorochromate complex, and it oxidizes primary alcohols up to aldehydes, but it still oxidizes secondary alcohols up to ketones. So I take a primary alcohol and I add chromium trioxide in pyridine with HCl. I form this pyridinium chlorochromate complex. I react it in the presence of methylene chloride, which is my solvent. The resulting product is the aldehyde. I've created one more carbon-oxygen bond, and this does not go on to oxidize to the carboxylic acid. Another example is taking 1-heptanol, PCC. I've just abbreviated all this stuff right now. Still using methylene chloride. I form 78% yield of heptanal, the aldehyde. How about tertiary alcohols? We've already mentioned that you cannot oxidize a tertiary alcohol any further, because to do that I'd have to break a carbon-carbon bond, and that would be combustion to form CO2. So chromic acid will actually oxidize primary and secondary alcohols, and I'll get that green color to form for chromium 6. But if I have a tertiary alcohol, that green color does not form. So let's look at different methodologies for oxidizing alcohols. If I have a secondary alcohol and I want the product to be a ketone, I can use chromic acid or sodium dichromate or PCC and get the ketone. If I have a primary alcohol and I want to stop at the aldehyde, I have to use the poison form of chromic acid, which is the PCC reagent mix. If I want to oxidize primary alcohols all the way up to carboxylic acid, again, I can use chromic acid, a strong oxidizing agent. Let's look at some examples. Here I have a molecule. It has a double bond in there. I have one secondary alcohol and I have a tertiary alcohol. Let's see what would happen if I oxidize using the sodium dichromate mixture and the PCC mixture. If I use PCC, I only oxidize the secondary alcohol up to the ketone. I do not oxidize the tertiary alcohol at all. If I use sodium dichromate, which is a strong oxidizing agent, I essentially do the same thing. I oxidize the secondary alcohol up to the ketone, and I do not oxidize the tertiary alcohol at all. In the second example down here, I have a secondary alcohol and I have a primary alcohol. If I use the mild oxidizing conditions of PCC and methylene chloride, I'm going to oxidize the secondary alcohol up to the ketone and the primary alcohol up to the aldehyde. If I use the strong oxidizing conditions of sodium dichromate in sulfuric acid, I'm going to oxidize the secondary alcohol to the ketone and the primary alcohol up to the carboxylic acid. There are other oxidizing agents that I could use. Potassium permanganate is a strong oxidizing agent. Nitric acid is a strong oxidizing agent, and they behave similarly to sodium dichromate and sulfuric acid. I oxidize primary alcohols to carboxylic acids. I oxidize secondary alcohols up to ketones. There is another chemical reaction that I can actually use to oxidize primary alcohols up to the aldehyde. That's called the Swern oxidation, which uses dimethyl sulfoxide, often known as DMSO, and oxalyl chloride, and a hindered base. So here are my reagents. Here's my alcohol. That could either be a primary or secondary alcohol. Here is dimethyl sulfoxide, which behaves both as a solvent and as a reagent. Here's my oxalyl chloride. Here is my hindered base, and here is another solvent that I mix in there, methylene chloride. When I do this chemical reaction, I form either the ketone or the aldehyde, depending on whether this is a primary or secondary alcohol. One of the products is dimethyl sulfide. I also get CO2, carbon monoxide, and HCl. So secondary alcohols oxidize to ketones, and primary alcohols oxidize to aldehydes. Very similar to PCC, but less toxic. If I use PCC or chromates, I get the chromium I have to dispose of. And chromium is toxic to all kinds of living organisms, both microorganisms and fish and birds. So if it gets into our environment, it is a toxic waste substance. So we often use this DMSO oxalyl chloride with a hindered base and do a Swern reaction. Let's look at the reaction mechanism for that. Here I have a primary alcohol. My lone pair of electrons on my oxygen are going to attack my electrophilic sulfur, kicking off chlorine. My chlorine acts as a base to deprotonate that complex. My amine comes in and actually removes my hydrogen that is attached to my carbon with the oxygen, and my electrons from a hydrogen go down to form a double bond and kick off my CH3SCH3 compound. Now you're saying, how do we know that this is actually happening? Scientists have actually isolated some of these intermediates, and so they have proposed this reaction mechanism. Okay, so if I take a primary alcohol in the presence of DMSO, oxalyl chloride, at minus 60 degrees, throw in some hindered base, I form the aldehyde. If I take a secondary alcohol, I form the ketone. Even though this is a very useful reaction, it is often very smelly because I'm using sulfur-containing compounds. If I take cyclopentanol and react with the Swern oxidation, I get about 90% yield of cyclopentanone, so secondary alcohol to ketone. If I take 1-decanol, primary alcohol, I get 85% yield of my decanal, my aldehyde compound. A fourth common reagent is actually using common household bleach. What bleach does is it oxidizes things. The oxidizing agent in most bleaches is actually this hypochlorous acid, HOCl. So if I take a secondary alcohol in the presence of hypochlorous acid, I'm using a carboxylic acid as my solvent, I get the ketone. If I take a primary alcohol, I get the aldehyde. The reaction mechanism for that is I have my lone pair of electrons on my alcohol. They react with the acidic proton on my hypochlorous acid. I then form a good leaving group here. So my oxygen of my oxygen chloride anion then attacks that carbon in an SN2 reaction. I then have this all set up where my chlorine is a good leaving group. I have base in solution, which can either be the water or it can be another molecule of the OCl. It removes that proton. I create one more carbon-oxygen bond to form the ketone. Let's do a practice exercise. And let's determine what an appropriate method, what are the appropriate reagents to use to accomplish the following reactions. For converting a secondary alcohol into a ketone. Well, I know I can use sodium dichromate or I could use Jones reagent. Both of those are strong oxidizing agents. I could use bleach, so hypochlorous chloride. I could use the PCC, and I could finally use the Swern conditions. All of these reagents will oxidize a secondary alcohol up to a ketone. How about oxidizing a primary alcohol up to a carboxylic acid? I need strong oxidizing reagent in that case, and that's going to be my chromium-based systems, my sodium dichromate or my Jones reagent. How about reacting a primary alcohol and stopping at the aldehyde? In this case, I could use bleach, my hypochlorous chloride. I could use PCC, or I could use the Swern reaction. You can see I have a lot of different options here for creating that reaction. Let's look at oxidation reactions at the cellular level, and let's look at three common alcohols. Let's first look at ethanol. Ethanol is typically consumed as a drink. It enters into the circulatory system where it is transported to most of the cells in the body. There are some enzymes at the cellular level called alcohol dehydrogenase, removing hydrogens or oxidizing the carbon up to the aldehyde. There is another enzyme at the cellular level which will oxidize the aldehyde up to the carboxylic acid. So ethanol gets transformed into acetic acid. Acetic acid is just vinegar. It's slightly toxic at the cellular level, and it also interferes with neuron communications, which gives people that drunk feeling by consuming alcohol. If I were to drink methanol, another small alcohol, at the cellular level there is an alcohol enzyme called alcohol dehydrogenase for methanol, which transforms methanol into formaldehyde, which is a glue and is highly toxic. There is a second enzyme which transforms formaldehyde into formic acid, which is toxic at a cellular level. It actually kills cells. So methanol is a very toxic thing to drink, and we don't have many people drinking methanol. Ethylene glycol, which is a diol, which is just antifreeze. At the cellular level, it gets oxidized to oxaldehyde, which gets oxidized up to oxalic acid, which is actually a poison also. The treatment for drinking ethylene glycol is actually to add a competitor at the cellular level by drinking ethanol. Let's look at the process of respiration. You might know that as either the Krebs cycle, the citric acid cycle, or modern day scientists called it the tricarboxylic acid cycle, or the TCA cycle. If I take ethanol and drink it, I can actually have it react with ADH, ethanol dehydrogenase. When I react that, something needs to be reduced, and so I reduce a coenzyme called NAD+, it gets reduced to NADH. Then I take another molecule of my alcohol dehydrogenase. I have acetaldehyde reacts with another equivalent of my coenzyme NAD+, which gets reduced to NADH, and this NADH goes on to form energy. So the oxidizing agent is a cofactor, or sometimes called a vitamin in the case of cellular respiration.